get started now. Okay, is this coming across the speaker? Okay. Let me just get this on again, and let's try one more time. Okay. Is it coming through the speaker or not? It is. People are convinced of that. Okay. So let's get started. First of all, let's first talk about the homework on the backtracking assignment. How many people here have working programs? Programs, okay, more than. How many people are able to do problems of up to, let's say, 10? A bunch of people. How many people are able to do problems of up to 15? A smaller number of people. How many people are able to do up to size 20? Roughly the same people. How many people can do up to 25? Looks like that's where we're hitting one person is still admitting it here. Okay? So we're still hitting walls there. You're going to hit walls eventually, so that's not necessarily bad. But let's talk a little bit more about the assignment, see if we can get any other pruning ideas or directions or anything. Any questions about the assignment, first of all? Yes? Are there going to be self loops or watch it, let me try this one more time because I don't think I hear me. Are there going to be self loops in the graph? I don't promise you that there's going to what you have is what you have. Okay, so if you want, you can check. I don't think I have self loops. I don't think I have any repeated edges. It wouldn't be terrible practice to check that. But what you have is what you have, right? So you can check that. Okay, but I don't think it's there. But depends what your level of hygiene is. Okay, you should check these kind of things. Any questions? Yes. For submitting it, you're going to print out a code and print out the output of your thing. Okay? That's what I want to see. And the ones that are fastest, that are going to be eligible for the contest, those we will demand electronic submissions from. Any questions? Yes?
So it's like when you say you're talking about the biggest graph, so should we just print out the biggest magnitude of vertices, and just because you have the different kinds of graphs too, like and some are I guess harder than others?
Okay, so I give you a couple types of graphs, and you are right in saying that certain graphs are going to be more difficult. One set of graphs will be more difficult than the others on different programs. I'm not sure I'm ready to say one is absolutely more difficult than the other, but I will say that they're going to have different characteristics that will. So I think what I want you to do is for all the sets of graphs that I give you, show me how far you get on that. Okay, so if by some miracle one set is unusually easy, you don't say, wow, I got this all the way. Let's just see where you sit. Yes?
For the answers you gave, you had a lower bound and upper bound. What are those?
Okay, those are the results of some program that somebody gave a few years ago to compute these. I don't know what the answers are. Okay? And what I think those are intermediate outputs spit out by their program. Okay, so I think that that's something you probably want to ignore. Okay, you want to look at the solution and see if you've got a solution as good as that solution is. That's, I think, the thing that matters. Okay? Any questions? Yes?
So you can just skip printing out upper and lower bounds?
You can skip printing out upper and lower bounds. Again, it doesn't hurt you for debugging purposes. Knowing what the upper and lower best upper and lower bounds you can find for the solution without search or when they change may help you know when how your backtrack search is proceeding. Okay? So that might be something that is helpful to you. Okay, in trying to get as far as you can get on it. Any other questions or comments about the backtracking program? Let's just talk about some other ideas that might lead to other pruning ideas. Let's just think about it. Does it matter what order the candidates are in construct candidates? Okay, let's do a little bit of thinking here. Remember, what are we doing? We have our construct candidates, okay, where we list all the possible candidates for the next slot. Does the order of those candidates matter? Okay? In terms of how long it runs for. Okay, who here says it does matter? Couple people. Who here says it doesn't matter? One or two. Who here says it depends upon how the rest of my program is written? Okay, some people, that one. But let's think about it intellectually. What would be what would you want, if you wanted to have the candidates ordered in a way that might help your search, what candidate should be on top of those possibilities? Okay? Is it one that is, what properties do you think you would want that one to have? Okay, yeah? Say that again? You say high degree, meaning, you're saying high degree meaning, you want to put the high degree one down quickly. Why is that?
So then when you do the pruning, it may we may already we may put it into the minimum now, so you don't have to.
Okay, so one possibility is that when you put down a high degree one, it will prune quickly. Okay, possibly. Okay? So what you want to do is to get the most pruning that you can quickly. And that sort of would mean that the most rejections of partial solutions. Okay? And maybe, depending upon what you're doing, maybe that means put the high degree vertices first, because those will be rejected quickly. But maybe it means something different. Maybe it means put the low degree vertices first. You want to ideally get what the right answer is as quickly as possible. This is one thing that I would tell you, right? If you knew what the actual size of the solution was, then you would be able to prune anything that was bigger than the right solution, right? If all you're coming up with are terrible solutions initially, it is harder to prune. You won't prune then as well as if you have a small solution. Okay? Does that make sense, what I just said? How many people thinks it makes sense? How many people don't think it makes sense? Okay? What should be clear is recognize that there is a degree of freedom you have in ordering your queue. And you may want to pick the most promising things usually it pays to put the most promising things first. Okay? Perhaps you want to put the least promising to reject them, although I think you're going to eventually reject everybody anyway. Okay? But does everybody see that that is some degree of freedom that you probably haven't exploited? How many people see that it's a degree of freedom? Okay? And that sorting it by some criteria might be a reasonable thing. Okay? Any other comments or ideas about that might lead to better pruning? Okay? The other thing that I encourage you to do, that just came up by some people who came by today, is some people have a pretty good idea that you're pruning, you get a partial solution, you see if this solution is bad, and if so, you're going to want to throw it away. Recognize that you don't want to throw it away on the basis of how bad it is. You want to throw it away on the basis of how bad it will be. Okay? It may be you can argue that even though you've put down a few edges, 5 vertices, and the lowest band edge so far is of length 3, you might be able to argue that there is going to be an edge of at least 5 as a result of what you've done so far. And that might be enough to backtrack. Okay? So the more you can think about how quickly you can argue that this is going to be bad and will not help me, that is the key to pruning it quickly. Any questions about it? Okay. Any other questions about that assignment? Okay. Going once, going twice. Okay, good luck on that. Keep beating on it. Okay, fair enough. So, unless there's other questions, I'd like to now shift gears into, we're talking here about backtracking. And backtracking is one of these things that I think you need to see a lot of example problems in order to get the idea of, okay? And so the problems of the day here are pretty important problems of the day. In fact, maybe we'll work this one out on the blackboard. Let's try that one here. So what is the problem of the day? The problem of the day here says that we're given 3 strings, okay? And we want to figure out whether or not there is a way to interleave the characters of the first 2 strings so as to make the next 2, the last string. So if we take a look at this here, the input here was chocolate and chips, okay? And we want to figure out, is there a way to interleave the characters from chocolate and chips to make this word? Okay? That's really what the question here is. Okay? Now, is there a way to do it? Okay? I claim for this word there is a way to do it. How do we do it? Okay? I believe that if we say, let's just take a look at it. CHIP S. Does that leave chocolate? C, now let's try that in another color. CHOCOLATE. Does everybody see that pulling this word, chocolates, or however else you pronounce it, represents an interleaving of the word chocolate and chips, okay? Where chocolate reads left to right and chips reads left to right. How many people see what I'm talking about? How many people don't understand this at all? Okay, what's he doing? Any question? Like, what do you mean? Okay? Now note that, is there another way to put chips? Does chips exist some other way in this string? Okay? Is there another chips in chocolate? Yeah?
Well, you could, the 2 C's at the beginning of the word could be...
Clearly I could have used either C to start it. What about either H? Okay? I could have defined chips, perhaps. You might say as CHIPES. Does everybody agree that's a way of spelling chips?
No.
No? How do you spell chips?
No E.
Okay, without the E. Very good. Okay, you got me there. Okay, you know the limits of my training. Okay, chips. Okay, CHIPS. Okay? Does everybody agree that's another chips? But if I use that chips, is what I leave chocolate? Okay? Does everybody see that once I've done it, now I've got CO is no longer chocolate. Does everybody see the problem? Certainly there's a problem of, can you make chips out of this word? Okay, there's at least 2 ways to make chips. Can you make chocolate? There's probably at least a couple ways of making chocolate. The question is there a way to partition the letters of this into chocolate and chips such that you're not using any letter twice? Okay? Does everybody see what the catch is? Why the first chips works and the second chips doesn't? Any questions about that? Okay? So what about chocoliptes? Is there a way to make this thing into chocolate and chips? Okay? And I guess what I would probably say is, no, why not? The P and the S are in the wrong order. That's, I think, enough of a proof. There's only one P and only one S. Okay? And they have to be PS. There's no way you can get chips out of this thing. Okay? Any questions about that? Now, the question is, do this algorithmically. Okay? Can someone give me an algorithm? Let's think about it. Can we come up with an algorithm, given again what our word was, chocolate? Chocolate, I guess it is, right? I've already proven my spelling credentials. Chocolate and chips. And I've got a target word, which is, let's say here, some complicated thing. Is there a way to make this interleave this with this to be this. This is x, this is y, this is z. Okay? Can I find a way for the given z, okay, is there a way to interleave these two words? Can I come up with an algorithm for that? Okay? Any ideas about, any question about what the problem is? Now, how can we do this? Can anybody suggest an algorithm for it? Let's start to think about what the problem is. In general, I give you two words. I want to find out, is there a way to interleave them to make this third word? Okay? Any ideas how we might go through it? Okay? Yes?
You can start with one of the words and take the first letter.
Yeah?
And see if it exists in Z. And if it exists in Z, then you take that first letter out and see if the other, if X or Y exists.
Okay, so what you're trying to say is, maybe what is this? Anybody read me what the last word is? I'm sorry, does anyone, what did I say the shuffle was on that? Can anybody read that to me? C, what was it? What's the output going to be? Somebody read it to me. C. C-H-O. Okay, no one's reading it to me. Let me just see if I can copy it back. Okay, let's just try it like that. What is it here? This would be C-H-O-C-H-I-L-A-T. No, that's the wrong one up there. Which one is it? Okay, let's try. C-H-O-C-H-I-L. C-O-C-H-O-C-O-H-I-L-A-P-T-E-S. Very good. Okay? So now let's come back here. I think we'll go back to this one again. Boom, sorry. Okay? So what are you saying? You're saying that somehow the first letter here, C, has to be one of those first letters. Now, which one is it? Or doesn't it matter? Let's think about it. Here you're telling me it doesn't matter, right? So you're going to say, look, C, they both begin with C. Let's pair them up arbitrarily, right? So maybe this is a C, this is a C, this is a, let's maybe try it like that. Here is a C, and here is a C. And now what are you going to do? You're going to say the same thing on the H, right? You've got this H. This H pairs up with those two H's. Which one should it pair up with? Does it matter? It mattered a few minutes ago. Okay? It is the case here. If you look at this case, if I paired it with the bottom H, there was no way to do it, if I remember correct. Okay, what are you trying to say?
I'm trying to say, if you pick up the original, the first C, if, let's say you say that you're testing for the word chocolate, if you take out the first C, you test if chocolate still exists inside that pattern.
Okay, I think I see what you're saying. Or maybe from this point, what you're really going to say is this. Let's say I put the H with this. Check to make sure there's still chocolate, what's left of chocolate and left of chips here. Okay? And you're saying if it doesn't make an immediate mistake, then move on. The trouble is, that's not an unreasonable thing. But it's not clear to me that just because chocolate and chips exist in here still, that there is a way to interleave them. When you did that match, you might have reused some of the characters. Okay? So you're trying to make a local decision now. That's a reasonable way to think about it. But he's trying to make a local decision now about who this goes to. And he's saying, if I can't see it making trouble for me, I can assign it. But I assert that isn't going to work, or if it's going to work, you'd better have a proof that it's going to work. Right? And I don't see that proof because I don't think it's going to work. Okay? Any questions about that reasoning? Any other ideas how we can go about doing this? Okay? Before I show you my way of doing this. Okay? Any other ideas? Yes? Do a recursive thing, okay?
So you take, if it's a shuffle or whatever.
Yeah,
Then the first, I guess you do first or last one has to be one of the two.
yeah.
The last letter, let's say, has to be the last letter of the first word or the last letter of the second word.
Okay, so what she's saying is she wants to do it recursively. She's thinking about, we could have done this, maybe an idea from the first word or the last, but I like the last letter better, just from a point of view, my cultural thing. So what she's, okay.
Yeah, so you take off, the last letter has to match one of the two.
She's saying the last letter, let's now start from the back of the strings, which is convention, not wildly different than starting from the beginning. But what's she going to do with it? She's saying this S has to match the end of one of the string characters. It could match this, it could match that. If there's a correct way to do it, the only hope in this case is to match that one, right? So in this case, there's no magic, okay?
So you would take off that letter from the B and also from the Y and then ask it from you.
Now I look at, now once I've done that match, there is a, a smaller string here, and now I'm going to recur. Can I do it on the smaller strings? Does everybody see that? It's now the same problem on a smaller string. The E, where could that go? Well, the only place where the E could end happens to be there. Okay? And now what are we going to do? The only place the T can go now happens to be here, right? The only place the P can go happens to be here. It looks like she's doing great, although she's not yet gotten to the big problem, the same problem that you're going to get. But let's get to that point, just to keep going. The P, we said, was going to be over here. The A, there's no problem with, right? The A has to be up here. The L has to be up here. We still have, she's doing well because she's working backwards, but she hasn't hit the hard part yet, right? The I is over here. The H looks like it's also got to be over here. Okay? Right? Now the O has to be over here. O. Right? No, what am I doing? Colors are bad. O is there. And now she's hit the hard part. Okay? Now she's got the same problem that you had before, which is she has a choice. The C can come from either this side or that side. Right? What do you do?
I'm not sure, but I think maybe if you take it from the same word every time, like decide if there's a tie, I'll always take it from X.
Okay, if you're saying, well, if I'm a tie, I'm always going to do this, then you need a proof of correctness. And your proof of correctness will be probably wrong. Okay? So if she can't, how do you figure out which one you try? Yeah? You do both. Okay? That there are two possibilities. Okay? Either it's going to come from this side or that side. Okay? And the question really is, you try one and see if you can finish. If you can finish with that one, that's great. If not, try the other one and see if you can finish. And this is now a recursive algorithm for it. Okay? So it's sort of like a backtracking thing right now. Does everybody see that? It's sort of like a backtracking thing. The only thing is, can we maybe get away by writing this recursive algorithm in such a way that things can be reused? Okay? And that's what's going to lead us to our dynamic programming. Okay? Any questions? So let's now look at how I would try to think about this from this kind of reasoning. What I like to do is to do my dynamic programming. I start by defining a recursive function that if I could compute it would solve my problem. Okay? Let's let S sub I j k equal true it said warning up here that this could be a Boolean thing. Let's just try it. Is going to be true if and only if x from 1 to I and y of 1 to j can shuffle to z sub 1 of k. Okay? Let's think what this says here. Suppose I define a function s with the property has 3 arguments. An index into I, an index I, an index j, and an index of k. Meaning a position in x, a position in y, and a position in z. Suppose this function is defined as true, that's true, in case we didn't see it, true, if and only if the first I characters of x and, just don't read that too well, that's supposed to be and, the first j characters of y can shuffle into the first k characters of z. Okay? Does everybody see that this defines a function that is either true or false for any I, j, and k? Okay, that much should be clear. That's by definition. If I knew how to compute this, would this help me solve my problem?
Yes.
You say yes. How would it help me solve my problem? Yeah?
Just input into that function the lengths of x, y, and z for I, j, and k respectively.
Does everybody see that if I had s of, this was supposed to be of length n, m, n plus m. Does everybody see that this is going to be a value that's going to be true or false, right? And this value is exactly what I want to have. Okay? How many people see that? How many people don't see it? Okay, any questions? A question like say that again would be a good question. Any questions? Okay? So it should be clear that if I could compute this thing, then I would know how to solve my problem. Okay? Now I want a recursive algorithm to solve this thing. Right? To compute this thing. Can anybody give me a recursive algorithm to compute this thing? Okay, S sub I, J, K. What is it going to be equal to? Okay? Yeah?
Well, it's equal to the and of 2 specific things. The first expression is S I minus 1 comma J comma K.
A minus 1, what are you saying?
I minus 1 comma J K minus 1 or S of...
Wait. So this thing?
Yeah,
Or what?
S of I comma J minus 1 comma K minus 1.
Okay, you want to let me wait. You want to say this is an or? You want to take the or of these two?
Yeah, just those 2.
Okay.
So that is the first expression, and I want to and that with another Boolean function.
And you want to take the whole thing here. This is an or.
Yes.
And what?
An expression that a function that basically asks is the ith letter
Is x sub I
or y sub j
or y sub j
equal to z of I plus j.
z of k. Okay, let's look at this and see what he's saying here and seeing if this makes any sense. Okay? To be honest, it doesn't make sense completely. But parts of it make very good sense, and this is where I want to take a look at this. Okay? Let's think about it, though. This is a good start to getting here. Okay? Why is it? Well, what's he saying here? He's saying that it would be great to know, if you want to know if you can do the first I and J characters, He wants to know, is there a way to do it up until the last character, right? That's what this is sort of saying, right? And he's defining this in terms of smaller things. That's recursion, that's good, right? But he's saying that either this or this has to be true, and either this or this has to be true. Okay? And actually, I see where he's now coming from. Okay? Do you see where he's coming from? It's not quite right, but it's actually closer to the right than I thought it was. Okay? Think what he's saying here. He's saying, if there's a way to match it up to the last character, and the last character matches the desired, the last character of one of the strings matches the target, then there's a way to do it. Did you kind of get that reasoning? If there is a way to get up to a certain point, up to match them except for the last character, and the last characters match the target, then there's a way to finish it. Okay? But there's a problem. What's the problem? Or
I think the ands and ors should be switched so that xi minus 1 should go in that and xi equals k, or the bottom.
the problem here is that which one of these characters matches depends upon what prefix is doable. Okay? So let me now write it the way I think I want to do it. Okay? I think it's going to be, okay, if it's this and x sub I equals z sub k, or, let's put this thing in big brackets, or this thing is equal to and y sub j equals z sub k. Now let's look at this and see if this makes sense. Now let's read it and see. The first I characters of x and the first j characters of k can be made to shuffle into the first k characters of z if there is a way to shuffle the first k minus 1 characters using I minus 1, the first I minus 1, okay, of x and first j of y, and the ith character of x is going to match the kth character of z. Then this describes a way to do it. We are going to match the ith character of x with the kth character of z, and then recursively use this solution. Does everybody see that? Or, if the y character, the jth character of y matches the target, we will have a solution if there is a way to match the first I characters of x and the first j minus 1 characters of y with the first k minus 1 characters of z. Okay? This is going to give us a solution. Okay? Either we will match it to x or we will match it to y. And we can do it if, after we've matched that character, we can solve the smaller problem recursively. How many people understand this equation and see what I'm saying? A bunch. How many people don't understand it? A bunch. Also a bunch. Any with questions? Okay. Any questions about this? Okay. Any questions? Again, see that it's a recursive thing. First, what should be clear? It isn't that complicated looking once you see it, okay? That much should be clear. It should be clear it is recursive, right? Recursive, okay? It is depending upon smaller things, okay? And we are saying I could figure out the answer to the whole thing if I knew the answer to certain smaller sub-solutions. Okay? That's what was necessary here. Any questions about it? I'm going to see a bunch more of these things, but I'm happy to ask for any questions.
What exactly was the dynamic solution?
Now, what would the matrix of this thing look like, you're saying? Okay, yeah?
It would be a three-dimensional.
This looks like it's going to be a three-dimensional matrix, which sounds frightening looking, but that's still a three-dimensional matrix. That isn't so frightening, right? And you're going to have cells I, each string's going to be of I, J, and K. What is I going to be between? What is this index going to range between? 0 and n, so there's something like n possible arguments here. What's this one going to range between? M. And what's this going to range between? Okay? So this tells me that I've got something like n. I have to figure out which is bigger. Let's say n is bigger than m, just for the sake of dealing with this, right? Then, well, what would this be? This would then be something like n squared m. Does everybody see that? Because m plus n if n is bigger than m, this is going to be at most 2 times that, right? So this is going to be order that many cells. Right? Does everybody see that we've got a matrix that's this big? How much time is it going to take to fill in each cell of the matrix? Okay. We're going to use this formula to fill in the cells of each matrix. Constant. Why is it constant? This is the ith element of the character array equal to the kth character of array. Constant test, right? Look this thing up in my matrix if it's already there. Constant. And them together, constant. Do the same thing again and OR it. Does everybody see that it takes constant time to fill in each box? Once you have this and this sitting securely in your array, in your matrix. Okay? So what is this going to do? It looks like it's going to give you an algorithm that is going to be order n squared m, because it's that many cells times a constant number of work per cell. How many people see that? Any questions about that?
So, maybe I mixed it, but, so what is this? So the Boolean value for each cell is the letters of the string?
The Boolean value of each cell is telling you, can you do it? It isn't telling you how you can do it specifically, but it is giving you what the Boolean value is a thumbs up, thumbs down thing, right? Yes, there's a way to shuffle these substrings. No, there is no way to shuffle these substrings, right? Now, it hasn't shown you how to actually find that, but hopefully that'll become clearer when we talk about edit distance and finding the parent, and that hopefully will be clear in a little bit. Yes?
That's easier both conceptually and electronically.
Okay.
Why not just have a two-dimensional thing and try to find a path from the top left corner to the bottom right corner where the vertical is, say, y and this is x, and you just add an extra column and then try to find a path through it?
Okay, so what he's saying is, why did you have this three-dimensional array? He's saying, I want to use a two-dimensional array. What are the 2 dimensions you want to use?
X and y.
X and y. And why don't we need z?
Because we're trying to find if z is a solution, right?
Well, what you're trying to say, I think, is that z is determined by x and y. Okay? So in fact, he's kind of right. Okay? That we don't need, in fact, do we really need to have that k index? Or what if instead I rewrote this thing a little bit? Okay? What if instead I viewed it as, erase that thing, Suppose I change my problem definition now to this. Is there a way to shuffle the first I characters of X to be the first J characters and the first J characters of Y so they equal the first I plus J characters of Z? Does everybody see that that's really the exact same question here? Okay? And that what's good about that is that's actually a win here. Now let's change our dynamics programming algorithm a little bit. This is going to go away like that. This is going to go away like that. This is going to become I plus J, right? That is exactly as correct as before. What is the running time of this algorithm now? Okay? Now it is going to simply be n times m. Right? So this is in fact much better than the other way I was doing it. Okay? So let's think about this for a minute. Okay? Because we're going through the logical development here to see what this, none of this is really magic. Okay? Does everybody see that in my recurrence I had a parameter I didn't really need? Have any of you ever written a subroutine where you had arguments you didn't need? Okay, you've done it too. Okay? But if you don't need it, if you eliminate it here, that's not going to, you have reduced the size of the possible sets of inputs, right? We're never going to worry about, is there a shuffling of the first one character of here and the first two characters of here that add up to a string of length 5. Before we would have said no, there was no way to do it. Now there's no need to say no, because we're not even going to ever ask questions like that. Okay? How many people see why this is an improvement? How many people still see why this is correct? Maybe it may even be easier to see why it's correct. I think it's actually easier to see why this is correct. Okay? Any questions? Yes? Why is it correct? Under what is the recursive idea that they're saying here? If we have two strings, let's make this thing chocolates chips. Okay, so we really add the problem and let's slap another S someplace. Okay? Under what condition is this string solvable by this string? This S is going to have to go to the end of one of those strings, right? If there is a way to have this and this go into this S has to go into one of those strings. It could be this string, it could be that string. But under what condition do we know it's right? We know that either this string is going to go to this string, and then what's left, namely the shuffling from here to this whole string to here, has to be possible. If so, then we were safe in assigning that, right? Or we would assign this to here, in which case that's what's left. Chip and chocolates is going to have to be able to shuffle into it. Okay? We know the end has to be this gets matched to one of these two. It can be matched there if and only if the rest of the strings, the smaller problem, also can be solved. Okay? And that's the recursive idea that we're talking about. Does that help you? Maybe. Okay? Any questions about that? Yes? Why is the complexity n times m? With what I'll say is all dynamic programming algorithms. Analyzing them in some sense is easy. It's the number of boxes times the cost per box. Okay? How many boxes are there? His array was only n by m cells. Does everybody agree with that? It's the length of x by the length of y. So there's n times m cells. Now the question is, what is the cost of doing this thing? If we have this value already stored up in a table, we can look it up in constant time. Right? This is a smaller case. If we've already solved the smaller cases, we can then solve the bigger case. Okay? Looking this case up, smaller case out of the table took constant time if it was in the table. Plus constant time, plus constant time, plus constant time equals constant time. Okay? That's why it's n times m time. N times m boxes times constant amount of work per box. Any questions? Okay? Any questions about this problem or this algorithm? We're going to see this all over again several times. Okay? But the basic principles here should now start to become clear of what you should start to recognize some of these principles. Any questions? Okay. So let's talk about what is probably the most famous dynamic programming problem in the undergraduate universe, okay, which is this problem of computing edit distance among strings, okay? And in fact, if you understood the chocolate chips thing, you'll be ahead of the game in understanding edit distance, okay? So what is the problem? A lot of things in computer science reduce to, or there are a lot of times when you want to match, okay, words that are not completely spelled right, okay? When somebody types in, you want to Google Skeena, okay? Maybe you'll remember how Skeena is spelled, but some people put in an extra N or reverse the E in the I, okay? How is it when you go to Google, you type in a misspelling, you likely will come up with my name, or even better, you try misspelling Obama's name. I'm pretty sure Google will get that one right, okay? Somehow there's notions of trying to, when you can't find an exact match of a string, to find one that is closely related to it. And that gets into this idea of edit distance. Okay, let me see if I can do this. Say ka-chunk. Okay, so misspellings motivate a problem which we will call approximate string matching, which is we would like to take a look at two strings and tell how far apart they are. Okay? Two strings that are identical, their distance should be 0. The bigger a spelling difference between the strings, we want there to be a bigger, in some sense, edit cost to it. And so a way to measure the distance between strings is something that we would call the edit distance. The minimum, to try to figure out the cheapest cost of converting one string to another. Okay, come back here. Bunk, bunk. So how can we change one string into another string? Okay? One possibility is you substitute a character. You meant to type the word shot. You accidentally typed a P instead of an H. You got spot. What is the number of changes it takes to convert shot to spot? Everyone will agree one substitution can do it. Okay? So how close are shot to spot to each other? They're one change apart. One substitution. How much of a change is it from a go to a gog? Okay? Again, this is one change. This change is an insertion. If I insert a G at the end of a go, I get a gog. One change. That's how far apart those words are. Yes?
This may be kind of trivial, but can we alter the way that it weights based on how far away on the keyboard they are for an instance of substitution?
So you're saying you have a different idea of what you call it, how far apart strings should be. You're saying some mistakes are more common than others. Like, for example, if you're typing them, you might slam the key next to it by mistake. And you'd like to say, well, if it's a nearby change, I only want to count that as half a change. Whereas if I had to be silly enough to reach across the keyboard to misspell it, I should be punished more.
You're assuming they're not using Dvorak keyboards.
So, but what is clear, he's assuming something about keyboards, but he's saying something actually quite meaningful. I'm going to show you for the case where, I'll work this thing out for the case where we're going to charge 1 for every operation. The truth is you could pick whatever cost you want for specific operations to customize this for your particular application. So a typing distance might be, as you suggest, whereas a spelling distance, like for example, C's and K's probably get replaced more often in spelling world, or S's and C's, right? Or S's and Z's, I'm guessing. Okay, and then you replace an S with a Z, an A with a Z. Okay? So you could define, I will tell you in general, this is an elliptical thing. Yes, you can define different cost weights. And in fact, I'll even show you where in my dynamic programming you would do that. Okay? But for now, let's just think about edit distance, where you get a 1 for a substitution, 1 for a insertion, or 1 for a deletion. See that there's somewhat of a difference between a deletion and an insertion. In an insertion, you go from the first word, you add something to the second word. In a deletion, you go from you take a character and in some sense add it to the second word, or equivalently delete it from the first word. Do people see that insertion and deletion are kind of symmetric? Okay? But they are different. If you're trying to transform one word into another word, you might use a mix of insertions and deletions. Let's say you wanted to convert, let's say S-K-I-E-N-A to skinas. Okay, to do this, the right way to do this is you should delete this letter and you should delete that letter, right? But you're deleting them from different strings. So the picture here is you delete it from here and you insert it from here. Okay, so insertions and deletions are symmetrical operations, but you might need a mix of them in order to get from one string to another. How many people see what I mean? Okay, any questions about that? So our problem of edit distance is to try to figure out what is the smallest number of changes that will convert one string to another. Why might we want to do this? Let's just think again about why you might want to take strings and convert one to another and find what the smallest number of changes is. Can anybody think of any such applications? Okay. Any reason why you might want to find the smallest number of changes between one string and another? Yes? Right, so one person, you type in supercalifragilisticexpialidocious with a couple of mistakes in it. Your spelling corrector would like to try to figure out which word is closest to it, right? So you'd like to figure out what's the smallest number of changes between this and a word in the dictionary. So that is kind of the problem. That is one of instance of the problem that we have here. Okay? Any questions? Another one that came up once to me that just gives you, this is a fairly versatile thing to want to do. I was once working on a system for, let's think of something you know how to do. How many of you have ever used diff, the Unix utility diff? Raise your hand. How many people have not used it? Okay, so you don't know. Fairly often, you were given two files, slightly different versions of something, right? You had a paper, you started working on it, and then you sent the mail home and you started editing it a little different. You wanted to know where do two versions of a file differ. That is exactly the problem of trying to find the smallest explanation of how does this text differ from another. So if you ever use the Unix utility diff, this is doing this kind of a computation. Any questions? Okay. It turns out to be something you want to do quite often. Okay. Any questions? Okay. So how do we find what's the smallest number of changes? Okay. We could use a recursive algorithm. We could, just like we were doing in the chocolate chips problem, observe that something has to happen with the last characters in the string. Okay? That if we wanted to convert this string to this string, something is going to happen with those last two characters. Either they are going to be decided that they should match, or it might be decided that one of these characters should be deleted, or it might be decided that there should be insertion, so effectively the other character is deleted. In the optimal way to transform one string to another, something is going to happen at the right end of the string. What we're going to do is try all three possibilities and then recursively solve the problem on the rest of the strings. Okay? And figure out which one of these gives the best one. Okay? So here is a recursive algorithm for solving the problem of edit distance. Now, is there a way to make this bigger? Control plus, kabunk. No, that's bad. Does anyone have an obvious way to make this bigger? Control plus, that's right, Control plus. Shift plus. Control plus isn't doing it. Okay, now let's try one more. Okay.
Maybe it's unpinch with the trackpad.
Unpinch with the track pin, God knows. Forget this. Okay, let's take a look at it though. Maybe you can read it here, because the punchline is in the red. Okay? What I'm going to claim here is that there are three ways things can end up. Okay? Let's try this here. If I want to convert cat into, let's take a look at it. It was let's say into cat. Okay? What am I going to do with the last letters? I claim that there are three possible ways I might do it. I might say cat to cat is going to end up on a substitution, and that this is equal to it, and it ends on a substitution. In which case, it's the cost of that substitution plus the cost of comparing CA into KA. That's one way it might end. Another way might be to say, I am going to delete the last T, okay, at a cost of one change, and then figure out the optimal way to convert the cat into ka. Another possibility is that I will try to convert a CA into a cat and then pay the cost of that deletion or insertion. Does everybody see these are the only three ways that I can possibly look at the problem? I think we know which one is best. But does everybody see that there's only three ways that the story can end up? We can decide to align the last two characters, in which case, because they happen to be the same, okay, the cost is 0. Suppose it was CAD into cat. The same three possibilities still hold, okay? I could spend 1 for a substitution to convert a D into a T, and then solve the smaller problem. I could pay 1 to delete this last T and solve that smaller problem. I could pay 1 to delete this D and then solve the smaller problem. The best thing for me to do is the best of these three possibilities. There is a cost to matching the last two characters. See what it says, match? Match the last two characters. If the characters are the same, the cost should be 0. If the costs are different, by my measure, it's going to be 1. By his measure, it's going to have something to do with where they sit on the typewriter keyboard. Okay? But assuming I have a function to tell me what the cost of converting one character is to another, the cost of ending on a match is that cost plus the cost of editing the smaller parts of the remaining strings together. Okay? If I end on an insert, I have to pay the price of that insert plus the cost of editing, if that's this case here. If I am going to pay this character got taken care of by my insert, I pay 1 for that plus the cost of editing this into this. Or I could end with a delete, in which case I've deleted this character, and then I pay the cost of editing this. Which of these three possibilities is best? Whichever one minimizes the total cost. The cost of the last operation, which is this, plus the cost of getting to that last operation, which is the recursive thingy. Okay? Any questions about that? Okay? Any questions about that? So if you look at that, this is a recursive algorithm. It's a recursive program for computing edit distance. String compare here is recursively calling string compare. And this is a recursive thing that's going to find what the best way to do it is. Any questions about it? Now, if you run this recursive program, something amazing happens. If you give it a computer to compute the edit distance of two strings, each of about 12 characters long, it will run forever. Because this is a recursive program. Okay? It's just no better than your backtracking program. If I did a recursive search where at every point I've got 3 possibilities and 3 possibilities. If I've got a tree of height 12 where there's a branching factor of 3, that would be 3 to the 12th, which is big. What?
It's a really big.
It's a big number. Okay? But I can do the same thing, not by making a recursive call, but by noticing that of my recursive calls, the arguments to my recursive calls are just the positions in the string. And there are only n choices for the first position in the string and m choices for the second position in the string. If I store these things instead of recomputing them, I am not going to get this giant bushy tree. Okay? I am going to have only n times m things that I'm computing, each of which I'm computing once. And I claim I'm going to be able to compute each one in constant time. Any questions? So let's instead look at the dynamic program. Okay? Note that I had a recursive program, but there are only n times m possible recursive calls because the arguments are all ij pairs. How far in each string did I get? If I store them up in a table and instead of recomputing them, then I can compute this quickly. Any questions? So what is my dynamic programming table going to look like? Okay? I'm going to define a table of n times m cells where each cell is going to have 2 numbers in it. One is the cost of getting to this point. The other of which is which direction did I get to this point? Which option did I pick of insert, delete, or substitute for that last change? So not only can I figure out what the cost of the 2 words are, but I can figure out how to convert one into the other. Okay? Any questions? We'll show you an example in a minute, and that may bring people back. Okay? In fact, let's take a look at the example here. Okay? First of all, here is a dynamic programming version, which I want you to look at offline when you can see it. It is almost identical to the previous version. Again, there are 3 possible choices at every possible ij position. I can end on a match, an insert, or a delete. The cost of the match or insert or delete are determined by the local characters at the end. The total cost is the cost of the last operation plus the cost of getting there. That was a recursive call. Now it's a previously computed thing in the matrix. Okay? Any questions about that? So let's look at an example and make sure we understand this. Okay? Here we're going to convert 2 strings, thou shalt not, into you should not. Okay? How many changes do you need in order to convert thou shalt not into you should not. Okay? You know, first of all, there may be lots of ways of doing this. This is not, may not be, it's not supposed to be necessarily completely obvious. Although I think in this case, it's maybe a little bit clear that you want to take either the H or the T, probably want to delete one of those, substitute this into, so there's one deletion, I think. The H is going to be converted into a Y, right? That's a second change. And now you've got thou into you. Should and shalt, what am I going to want to do? I probably want that A to become an O. I want to insert a U. Does everybody see that? There is another substitute and another insertion. And what, am I done yet? No, I guess I also have to substitute the T into a D. Does everybody see that in fact thou shalt not is 5 changes away from you should not? But how can we do this with dynamic programming? Do people see that? That thou shalt not to you should not, 5 changes. But how could we find this out? Let's go back and look at this matrix. This matrix is going to tell us what is the cost of converting a prefix of this word into a prefix of that word, right? How many changes does it take to convert an empty prefix of you should not, just the empty string, into thou shalt not? Suppose I want to convert thou shalt not into an empty string. What is the most effective way to do that? Okay. Let's just
delete 14 times.
Do you agree that if I took this and I deleted this 14 characters, I would convert thou shalt not into an empty string? Is there any more effective way to do that? How?
Put a null character in the first position.
Well, you say put a null. Okay. I could put, if I just wanted to get a null character to match a null character, then you're right, I could insert one in. But null, here I mean the empty string, not a blank character. Okay? So what is this matrix saying? If we view this as being the empty string, it costs a cost of I to delete the first I characters of this to make it equal to the empty string. Do people see what the interpretation of this column is? This column is going to tell us the cost of converting the first I characters here into the first J characters here. If J is equal to 0, this string is going to be empty, right? And then the only way we can convert a text into an empty string is to delete all those characters. How many people are with me? How many people are not with me? This part's supposed to be simple, and I don't think I explained it well. So if there's a question, I'm willing to hear a question, like say it again. Any questions? Okay, so we should know now in this table where this 1 through 14 come from. Any questions from where that 1 to 14 comes from? Now, what's the cost here of converting an empty string into you should not? The only way I can do that is 1 by 1 insert Y-O-U space S-H-O-L-D, okay, space N-O-T, right? Does everybody see that this basis condition, this row here, is defined in general by this the cost of editing an empty string into I characters?
Oh, good. Now I have all our base cases set.
Good base cases. Now let's look at the end of this thing. Okay? Let's look at the bottom down here. What is the final row element in this matrix equal to? This is the cost of editing thou shalt not into you should not. I say it's got 5 changes here. Why do I say it's got 5 changes? I claim there are three possible ways I could have done this. I could have found the cheapest way to edit "you should not" into "thou shalt know," and then add a T to the end of that. Right? It's one thing I could have done. The cost of editing "you should not" into "thou shalt know" is how much? Read the matrix. What is the cost of editing "you should not" into "thou shalt know"? What is the cost of that? Okay, yeah. 6. Why is that? That is where we are here. This matrix is getting all "thou shalt not" into "you should know." So one way I could have gotten this was by adding one insertion to the cost of getting here. So I had a way of getting to this thing, matching the two strings at a cost of 7. Or I could have done this. I could have instead chosen to get to here. That's the cost of what? "You should know" into "thou shalt not." I could have done that. That would have cost me 6 plus the cost of adding this T to the end of it, or 7. There was one other possibility, however. I could have edited "thou shalt know" into "you should know" at a cost of 5 and pay the price of substituting this T into that T. How much does it cost to convert a T into a T? 0. So the total cost of this was 5. This was the better way to get there. And that's why this thing is 5. Any questions about that? Okay. Any questions here? Let's come back and look at this matrix again. If you look at this thing, okay, what is the cost of editing? Let's try some other ones here. What is the cost of editing a string that consists of a Y into a string that consists of an H? Okay? I have 2 possibilities, 3 possibilities. I could delete the T and then insert a Y. That would have been 1 more than this, or 2. I could have deleted a Y and inserted a T. That would have cost 1 plus 1. Or I could have edited an empty string into an empty string at a cost of 0. And then done a substitution of a T for a Y. That would cost how much? 1. The cheaper of 1, 2, and 2 is 1. The best way to do it is at cost 1, which is what I have done here. Any questions? In general, this is the picture, and maybe now let me get back to the general picture. In general, we want to know the cheapest way to edit the first I characters of this into the first J characters of that. We have 3 possibilities. We could end on a substitution, okay? In which case, if we ended on a substitution, we want to know the cost of going from I-1 to J-1 plus this last character transition. That would be one way of doing it, right? Another possibility is to edit up to here the first I characters of this into the first J-1 characters of that. And then insert this J at the end of it, so it's 1 more than that. Or we could have edited the first I characters of this into the first J characters of that, and then appended the ith character from here to the end of it, in which case it's 1 more than that. Does everybody see that there's 3 possible ways to end here? as there are at any given position in the matrix. And the choice of the right one depends upon the 3 cells that surround it and what the characters are at that position. Okay? For whether I have an exact match or a substitution. How many people are with me at this point? How many people are not with me at this point? Any questions about it? Okay? So what does this mean? Take a look at this thing. What's kind of neat about this is that there is again, we have a matrix. The right editing distance here can be the right way to convert them is converted by seeing what was the path that we took from our end cell back through this matrix. At each point we chose one of 3 possibilities. Each cell has in some sense a parent. Which one of the 3 directions did it come from? Picking, if we went back through what those parents were, that would trace a path in this matrix. Does everybody see this? That there's sort of a path in this matrix that is defined by what did we do at each step through this matrix. Okay, to get to this point. This is the cost of editing thou shalt not into you should not. At each point we took the best of 3 options. The best of 3 options gave us a previous cell. To get to this place we took the best of 3 options. By tracing backwards from that we can work back to see exactly what were the transformations of one string into another. Okay? Any questions about that? Okay? Any questions about this? If you look back on what I said way back when, I said that we are going to keep a cell, our cell representation is going to be a cost and a parent. The parent here is which of these directions did we come from? The cost is what was the cheapest way to get there. Okay? And we're going to work through and figure this thing out. Okay? Any questions about that? Okay? Think about this, but let's just review what we have done. Okay? There's several places where you might be confused at this point. Let's go through them to see so you can pinpoint exactly where your confusion is. The first thing is maybe you don't see the recurrence relation. What was the recurrence relation? I guess I didn't really write it out for you. But really the recurrence relation is what? The cost of editing the first I, okay, let's try this down here. The cost of editing the first I characters of S into the first J characters of T. What was that going to be?
The minimum of 3 options.
It was the min of 3 possibilities. What were those possibilities? Okay. It could have been I ended on a substitution. If so, I cared about the cost of getting up to the point where I substitute. Right? Plus the cost of the match of what? S sub I into T sub J. Right? This is the cost of getting to the point of the substitution. This is getting up to that cell. This last term is, do I pay 1 because the characters are different or 0 because they're the same? The other possibility is that I instead ended on an insertion. In which case I pay 1, the cost of my insertion, plus the cost of getting there. Or I end on a deletion, in which case I pay 1 less than that. So one area of either confusion or clarity. See why this recurrence defines the edit distance. Okay, that's the first point you have to understand. Once you see that, the second point of view is see how you can build a table to hold these ij values, the cost values, C sub ij values for all I nj. What is the runtime of this recurrence? Well, we have n times m boxes if the string is of length n and m, and each box we fill in constant time. So the total algorithm running time is n times m. Any questions about that? Okay? Think about it. Okay? Take a look at these things and let's talk more about it next time. Thanks for your attention. Talk to you guys then.